All right, let's talk about one of the most famous equations in history. You've definitely seen it. It's probably burned into your memory from math class. But today, we're going to look at it in a completely new light, not just as a formula, but as an incredible story of discovery.
So, what if this isn't just about triangles on a chalkboard? What if it's an invisible thread connecting ancient builders, Greek philosophers, and even the phone or computer you're using right this second? Let's pull on that thread and see just where it leads us. And our story begins, as so many great stories do, with a little bit of a mystery. A mystery about who we should actually thank for this brilliant idea.
It's kind of funny, you know? We all call it the Pythagorean theorem, but the core idea was actually around long before Pythagoras. An Indian mathematician, Bodhayana, described this exact same relationship way back in 600 BC. But it's Pythagoras who gets most of the credit, probably because he's the one who formalized the proof and really made it famous in the Western world.
Okay, so let's get right to the heart of it. What is this theorem actually saying? To really get the plot, first we need to meet the main characters.
First up, the star of the show, the hypotenuse. Now, anytime you've got a triangle with one of those perfect L-shaped 90-degree corners, that's a right-angled triangle. The hypotenuse is always the longest side. It's that slanted side, right across from the right angle. And in our equation, this is our C.
And what about the other two sides? You know, the ones that actually form that 90-degree corner? Simple. We just call them A and B. And honestly, it doesn't matter one bit which is which, as long as C is always the long one, the hypotenuse. And all of that brings us to the main event, the iconic formula itself. A squared plus B squared equals C squared. It's simple, it's elegant, and you're about to see just how incredibly powerful it is. But, you know, saying it is one thing. How do we actually know it's true? Well, forget about complex algebra for a second. I want to show you a proof that you don't calculate. You just see it. Here's the secret. The key to really getting this theorem isn't about the length of the lines. The magic, the big aha moment, happens when you start thinking about the squares you can build on those lines. So check this out. This whole thing isn't just about length. It's about area. It's saying that the area of the square on side A plus the area of the square on side B adds up to perfectly equal the area of the big square on the hypotenuse, C. And that visual gets to the heart of the formal definition. It's not just a string of numbers, it's a real physical relationship. The two smaller areas literally add up to create the bigger one. It's an idea you can actually see, not just calculate on a page. Okay, theory is awesome, but the real power of this theorem is in what it lets us do. So let's take it out of the textbook and throw it at a real-world problem to see how this ancient rule can solve a totally modern puzzle. So imagine you've got a ladder leaning against a window. Now, keeping the bottom of the ladder in the exact same spot, you tilt it over to the other side of the street so it rests against another window. If you know the ladder's length and how high it reaches on each wall, can you figure out how wide the street is? Absolutely. Here are our numbers. The ladder is 17 meters long. That's our hypotenuse, C, and it doesn't change. In the first position, it's reaching a window 15 meters high. In the second, it's reaching a window that's 8 meters high. Our mission is to find the total width of the street. So for that first position, we just have to rearrange the formula a little. We know C squared minus A squared gives us B squared. So 17 squared minus 15 squared is 64. The square root of 64 is 8. Boom! That first part of the street is 8 meters wide. Now for the other side of the street, same ladder, same logic. We take 17 squared, but this time we subtract 8 squared. That gives us 225, and the square root of 225 is 15. So the second part of the street is 15 meters wide. And finally, the easy part. We just add our two results together. We've got 8 meters plus 15 meters, which gives us our grand total. The street is exactly 23 meters wide. Simple, clean, and solved with a 2,500-year-old idea. But the theorem doesn't stop there. Oh no, it has some really cool extensions. Think of them as power-ups that make it even more useful. First up, we've got Pythagorean triplets. These are these beautiful, perfect sets of 3 whole numbers that fit the formula exactly. No decimals, no fractions, just clean whole numbers. They're like the theorem's greatest hits. The most famous triplet of all time is 3, 4, 5. 3 squared is 9, 4 squared is 16. Add them together, you get 25, which is exactly 5 squared.
And hey, notice the numbers from our ladder problem? 8, 15, and 17? Yep, that's another classic triplet. Ancient builders actually used these triplets with knotted ropes to create perfect right angles.
And finally, there's the converse. This basically flips the logic. If you already know the lengths of all three sides of a triangle, you can use the formula to figure out what kind of angle you have. If a squared plus b squared equals c squared, you've got a perfect right angle. But if it's greater than c squared, you have a sharp, acute angle. It turns the theorem into a kind of geometric detective tool. So from one simple rule, you get the power to measure streets, build perfect corners, and even classify angles. It's pretty amazing. And it makes you wonder, if this ancient secret governs the simple shapes we draw, what other, bigger things in our universe, from the path of a light beam to the very fabric of space-time, does it also secretly govern?